Well, welcome back to Math 118. Today we start looking at Chapter 10, which is going to cover systems of equations, okay? And now there's a bunch of different approaches, right, to sort of firm up and study these constructs. But for this lecture, we're just going to sort of look at um, in a sense, what is like the traditional starting point before we get into different ways to represent them and kind of do it faster, okay? And first we're going to look at the case of two variables, but before we get ahead of ourselves, why don't we define some terms? So we have our definition. We have that a system of equations that's the first thing we're defining, so I'll highlight it. It's a set of equations which involve the same variables. And we'll see lots of examples of these over the next couple weeks. Sort of refining this a little bit, we have that a system of linear equations is just what you would expect. It's a system where each equation is itself linear. For the most part, this is what we're going to be studying. Dependent on time, we might do a little bit of lecture right at the end, looking at nonlinear systems. But for our sake, we can restrict ourselves almost exclusively to studying systems of linear equations. Okay? And we say that a solution to a system is an assignment for the variables, right? Because we have that our system, right, and it involves some set of variables. So it's an assignment for the variables. That makes every equation in the system true. Okay, hopefully that makes sense. If it doesn't, we'll dive into an example right here. So let's get ourselves an example, okay? Let's consider this system here. We'll say 2x minus y equals 5, okay? And we'll say that x plus 4y equals 7, okay? Now, both of these are linear equations, right? But we can consider them grouped together into a system, right? And we'll go over how to solve this in a second. But first, I want to show you, sort of what a solution would look like, right? Okay, so this is the solution to this system, okay? It's the ordered pair 3, 1, right? This first one is the x value of our solution, and our 1 is the y value of our solution, right? And we want to do two things here, right? First, let's actually verify that this works, right? So let's check our answers. We'll check with equation 1. It's going to be 2 times 3 minus 1. Well, 2 times 3 is 6. Minus 1 is indeed 5, so we're good. And checking with equation 2, we're going to have 3 plus 4 times 1. And that's 3 plus 4, which is indeed equal to 7. Okay. I want to draw your attention to one other thing real quick. Okay. And that's a geometric picture of what's going on. And we'll expand this geometric picture a little bit later in this lecture. But let's call this first one the purple equation. If we were to graph the purple equation, we'd get something like that, okay? And if we were to call this second one, say this yellow equation, we would get something like that, okay? And you'll notice that these two lines intersect at a single point. And that single point that they intersect at is 3, 1, okay? And that's because, right, each of these are a line, right? So then the points, x comma y, where this holds and this holds, is precisely where those two lines intersect, okay? So now that we have an idea what we're kind of dealing with, okay, let's get into how to actually solve these. And here's the first one. It's called the substitution method. And let's get ourselves a system. Let's say 2x plus y equals 1, and 3x plus 4y equals 12, okay? We'll call this one equation 1, and we'll call this one equation 2, okay? And we're going to break this into a series of steps, okay? For the substitution method, our first step is to solve for one variable. After we do that, we're going to do the thing that the name tells us, and we're going to substitute. And then finally, we're going to back substitute. And before we get on with this, I did notice this should be a 14. I don't know how I read my notes that wrong. But we want to start with picking one of our equations and solving for one of the variables in that equation. Right? And it would seem like to me the most natural choice would be to choose equation number 1, right? And then to solve for y, because the coefficient of y is 1, so we don't need to worry about dividing anything, okay? So that means that equation 1 gives this. Equation 1 says that 2x plus y equals 1. That also means that y equals 1 minus 2x, okay? And here's where this method gets its name, the substitution step. What we're going to do is we're going to take our remaining equation, in this case equation 2, and we're going to plug in this value of y for it. Because when we do that, we're left with just a linear equation in x, okay? Let's look at it. We have 3x plus 4 times y, but y has a new name. It's 2x minus 1, okay? And that's equal to 14. But as I said, right, this is now a linear equation in x, right? We have 3x plus 4 minus 8x equals 14, right? And then that's going to give us that minus 5x equals 10, or x equals negative 2, okay? So now what do we want to do here, right? Now we have a value for x. So what this tells us is that the solution for this system happens at x equals negative 2. So then what's the y value associated with it? Well, we know that if our system has a solution, and we're shown here that it does because we can find an x value for it, well, then these two lines should agree on that point, right? So we can plug this value of negative 2 into whichever equation you want, okay? But rather than messing around with plugging it in here or here, why don't we plug it into this one, right? Because then we don't need to manipulate y at all. And further than that, and we also know that this equation is equivalent to equation 1, right? You just move this 2x over, okay? So that's what we mean by back substitute. We take this solution and we substitute it back into our system, okay, to get that y is 1 minus 2 times negative 2, right, or 5, okay? So this gives us our final solution. the point -2, 5, right? Where -2 is our x value and 5 is our y value. Let's take a look at another way to solve these. It's called the elimination method. Okay. The substitution method is very, very useful for solving systems with two equations. But as we'll see in sort of the next part of this lecture, it gets a little bit fussy when you start moving into, systems of 3 equations or 4 equations, right? And it turns out that the elimination method tends to stay a little bit cleaner when you start adding on more and more equations, okay? So let's get ourselves another system. Let's say 3x plus 2y equals 14. And let's say we have minus x plus 2y equals -2, okay? And just as before, I'll give you the steps, okay? We're going to start by adjusting our coefficients. Right? And then once we've adjusted our coefficients exactly to where we want them, we're going to actually add the equations together. Okay? And then once we've added the equations, we'll end up with some sort of equation, and we can solve that for the remaining variable. Okay? And then just as before, we're going to back substitute. So our goal here with step 1 is to adjust the coefficients of this, okay, so that when we add them, one of our variables is going to cancel, okay? And we'll show this a little bit more explicitly a bit later, and we'll go over the different things you can do. But it turns out you can multiply an entire equation like this by some constant, and it won't change it, right? Think about a line, right? The line x equals y is the same line as the line 2x equals 2y, right? So we can multiply by constants without changing it, okay? And here's what we'll do. We'll keep equation 1 the same, but we'll multiply the second equation by -1, right? Because I see that we have 2y and 2y here, okay? And that would seem to me like the easiest thing to cancel. And so, but the thing that's keeping us from being able to cancel them is the fact that we have plus 2y here and plus 2y here. So if I multiply this equation by -1, I'm going to get x minus 2y equals 2, okay? And then when I add my equations, here's what I get. 3x plus x is 4x, right? 2y minus 2y is 0y, so that one goes away. And we have 14 plus 2 is 16, right? But now we have an equation in x. And in fact, we can divide both sides by 4 right away to say that x equals 4. Okay? So now we go through step 3, and we back substitute this solution into one of our equations. Okay? Why don't we pick number 2 this time, just because, well, my x isn't multiplied by anything. As we said last time, it is, in a sense, an arbitrary choice. As when these two equations agree, they agree, right? So we can plug it into whatever. But it looks like we're going to get -4 plus 2y equals -2. Moving that 4 over, we get that 2y equals 2, or that y equals 1. Okay? So once again, we have our final solution. In this case, it's the 0.41. Now let's try this sort of tactic on another equation or another system, okay? Let's try, say, 6x minus 3y equals 3, and say 2x minus y equals 4, okay? So starting with number 1, I want to adjust my coefficients, okay? And I'm noticing that, let's say we want to cancel y again, okay? We want to get this to be a positive 3, so we're going to multiply equation 2 by negative 3. 6x minus 3y equals 3. And it turns out that going forward, it will be really helpful for us to actually write down the multiplication that we're doing, right? So we're multiplying equation 2 by negative 3, okay? And then so when we do that, we're going to get negative 6x plus 3y. That's going to equal negative 12. But you might have already seen the problem here, right? When we add 6x to negative 6x, we get 0x. When we add negative 3y to 3y, we get 0y, and that equals 9, okay? It's a bit of a problem, right? Because that means that 0 equals 9, which is a problem, right? Because 0 most definitely does not equal 9, okay? But here's what I want you to think about. What are the graphs of these? If I were to graph them, here's what would happen. Okay, let's call this first one number 1. It's going to have intercepts at negative 1 and 0.5. Okay, so it would look something like that. If I called this guy number 2, right, it's going to have intercepts at 2 and negative 4. And so he's going to look a little something like that. Okay, and this guy is a little bit off, so I guess I'll get him closer. But you'll notice these lines are parallel, right? So there's no way that these are ever going to touch, right? Because parallel lines are never going to touch each other, right? And since they never cross, our system has actually no solution. And so let's sort of seek to categorize what happens here, okay? So let's take a look at the number of solutions to a system, okay? And it turns out actually to be fairly clean. There's only 3 possibilities, okay? So that we have for a system of 2 variables, we'll worry about more variables in the second part of this lecture. We have that exactly one of the following is true. Okay. Our first option is that the system has exactly one solution. Okay. Our second case, okay, is that the system has no solution. Okay. In this case, we call the system inconsistent. And option 3, the system has infinitely many solutions. Okay. Case 2 of infinitely many solutions we call dependent. And that's what's really interesting, right? Is either there's no solution, one solution, or infinite, right? There's no way that we could get 2 solutions or 3 solutions. And I want you to have a thought, why? Okay. And the reasoning for this is deeply ingrained in the fact that our equations are linear. Okay. Can you have 2 lines that touch at exactly 2 points and no more? And if you think about that for a little bit, it becomes kind of clear that, well, no, the moment a line touches at 2 points, they have to touch at every point because 2 points uniquely define a line. Okay, let's get a little geometric picture of this, right? So for our first case, we might have some line like this and some line like this, right? They meet at exactly 1 point, so there's exactly 1 solution. The case of an inconsistent system is what we actually just saw, right? In our previous example. We have 1 line, and then our second equation is for a line that is parallel to that original line, right? These parallel lines are never going to touch, so our system is inconsistent and has no solutions. Our final one is a system that has infinitely many solutions, right? And as we just said, the moment you have 2 solutions that are the same, you necessarily have infinitely many solutions because 2 points define a line, right? So the geometric picture in this case is that both equations describe not only parallel lines, but actually the exact same line. So they meet at every point, okay? So I've got 2 more examples for you in this part, okay? And we have the following system. 3x minus y equals 0, and 5x plus 2y equals 22. Okay. We're going to use the elimination method on this. And it would be a little annoying to multiply 3 by something in order to get it to 5, right? We would have to deal with fractions. So let's instead multiply this -1 by 2, right, in order to get this to be -2y. Okay. So we'll just sort of denote that like this. That's going to come out to 6y, or 6x, minus 2y equals 0. And then our other one's going to stay the same at 5x plus 2y equals 22. And now we're going to add these 2 equations, right? 5 plus 6 is 11x's. We have 0 y's and 22, okay? You can read off this 22 divided by 11 is 2, okay? So now we want to back substitute. And why don't we plug it into this one because our y is all on its own, okay? So we're going to have 3 times 2 minus y equals 0, or we have that y equals 6, okay? So that means that our solution is going to be the 0.26, okay? I do encourage you, again, go ahead and graph these lines and to check our work sort of geometrically. I know that I said that we had 2 examples before. For the second time today, I did not read my notes correctly. So we actually have 2 more examples right now. Okay, this next one is fairly short. So we're going to have 8x minus 2y equals 5, and say minus 12x plus 3y equals 7. Okay, it's not quite as obvious what we should multiply here in order to get everything to work out correctly. Notice we have fairly large numbers attached to our x and comparatively smaller ones attached to our y's. So let's try and cancel these y's. Okay, we can multiply the top one by 3 and our bottom equation by 2, right? This looks like 8 times 3 is going to be 24 x's, and we're going to be minus 6 y's equals 15. And then we have 12 times 2 is minus 24 x's plus 6 y's equals 14. And you may already see the problem, because when we add these, we get 0x plus 0y equals 29, or a contradiction, 0 equals 29, right? This is bad, so we have no solution, or if you prefer this vocabulary, this system is inconsistent, okay? One last example for this part, okay? And wouldn't you know it, it's another system of two equations. We have 3x minus 6y equals 12. We're going to have 4x minus 8y equals 16, okay? Once again, it is a little bit tricky for us to figure out exactly what to multiply this to, but our coefficients of y are both larger than our coefficients of x, so why don't we just try eliminating our coefficients of x? And so we can multiply the top one by 4 and the bottom one by 3, okay? That's going to make this top one 12x minus 24y. 12 times 4 is 48. What's our bottom one going to become? Well, we're going to have 12x minus 24y equals 48. And your first thought might say, oh, this is inconsistent, right? Because we have the same stuff here. But we actually have the same stuff here as well. So what this is telling us is that it's not that these two lines are parallel and never touch. It's that these two equations here actually represent the exact same line, right? So that means that our solutions look like all the points on that line, okay? We still want to try and write them out in, the form of an ordered pair, okay? And here's how we're going to do that, okay? It might seem a little counterintuitive at first, but sort of stick with me. Let's take whichever representative we want because they're identical. 3x minus 6y equals 12, okay? And let's solve for y, okay? We're going to get that 6y is 3x minus 12. If we divide both sides by 6, we have that y is 1/2 x minus 2, okay? So this is our line that categorizes all of our solutions, okay? And we're going to do what's called parameterizing the line, okay? That's a piece of vocabulary that you don't need to know, but it is the technical term for what we're about to do, okay? So let's say x equals some other variable t, okay? We're seeking to put this in terms of a new variable. So let's say x equals t, but if x equals t, then we have that y is 1/2 t minus 2, okay? So if we let t equal any real number, right, then our point on the line, right, some solution, is given by the relation the point t, comma 1/2 t minus 2, okay? And that's for all t in R, right? This is a categorization of the infinite family of solutions, right? If you pick specific values of t, you'll always get a solution. right? If you say picked t equals 1, right, this would become 1 comma 3 halves, right? If you picked t equals 4, right, this would become 4 comma 0, right? This is how we list our infinite family of solutions as an actual ordered pair rather than just an equation like that. Okay, so that's going to wrap it up for part one. Go ahead and jump on over to part two, where we're going to see how these ideas generalize into larger systems.